Alrighty. So we will continue with this derivative stuff and looking at some curve sketching and second derivatives, all of that. I did get some problem videos just posted this morning from section 3.4. And I have all but one that I wanted to put up there. And so at least that much is posted. My plan is this evening to work on grading exams and getting word back to you, well, no later than Monday before class, but actually, if I can, I'll try to get word back sometime tomorrow on exams. And okay, any questions over material? Anything? Yes, ma'am.
I had a question about the homework, the 3.4 section.
Uh-huh.
The 45.
Number 45 and 3.4. Yeah, okay, so these are some of the technology ones, and you know, as you're looking at that, what you're going to run into most likely is that you aren't going to be able to solve the equation very well. You know, that's why it's a really good technology problem. That's just, you know, when we first started having technology and so forth, a lot of the problem in many textbooks was they might say this is a technology problem, but it's one you could do without technology, and that's kind of silly. You know, but something like 45, my guess is it's not going to be too obvious how to get an answer to this when we take the derivative and set it equal to 0. So we have f of x is sine x minus 1/3 sine 3x. And then I think it was plus 1/5 sine 5x. And we're on the interval 0 to 2 pi, closed interval, 0 to 2 pi. And, no, sorry, 0 to pi. And so we want to find all our relative extrema. That's, you know, and they say graph the derivative and the second derivative and so forth. Well, so in this case in particular, the first and second derivatives are a piece of cake. I can do those. I've got a chain rule involved here, but other than that, my derivative of sine is the cosine of x. And then, well, it's the same thing here. So I'll have the 1/3, I'll have the cosine of 3x. But in this case, I need to remember to multiply by 3 the derivative of what's inside, plus my 1/5 sine of 5x times 5 again. Whoops, not sine, cosine. Okay, so there's the derivative, and of course I can simplify that a little bit. Cosine of x minus cosine of 3x plus cosine of 5x is equal to 0. And now what we'd like to do is get our critical numbers on the interval from 0 to 5 pi, or 0 to pi. I got no flipping idea, right? 0, you know, cosine of 0 would be great, you know, if x was 0, except things don't match up because, you know, cosine of 0 I get 1, but here I get 1 and minus 1. Oh, great, it's looking like 0, but then I get a plus 1, you know. So I have no idea. And so you need to solve it numerically. And at least in this case, where our interval is 0 pi, the easiest thing to do is go to Desmos. And now, actually, what I suggest, since they say, oh, plot them and take a look at them, I would actually start with f of x and just say, you know, f of x is equal to sine x and then minus 1/3 sine of 3x, whoops, or 30. Sine of 3x and then plus 1/5 sine of 5x. And so we just want to look between 0 and pi, so you know we're kind of interested in here. Let me go to projector mode, make that show up a little better. You know, so 3.14, you know, somewhere in here. And, you know, as I look at it, I see lots of possibilities for inflection points. And, you know, over here on the left, I kind of doubt that's a maximum there, but it might be. It might actually go up and then come back down. Well, quick way to check. I set it equal to 0 simply by looking at the graph. So I'll look at the graph of f prime of x and ask where f prime of x is 0. And, well, it's 0 right there, 0 right there, and 0 right there. And so pi over 6, you know, and this is the amazing thing with this particular problem is, for one, it happens to occur at these really nice angles, pi over 6, pi over 2, and 5 pi over 6, which I certainly didn't see that coming here in this. And then the other amazing thing is that Desmos tells you it's pi over 6. It doesn't give you some numerical approximation. It just said, hey, it's pi over 6. And so, you know, I've got those three numbers for my critical numbers, and that's what I'm going to have to do. You know, because I'm not going to come back to the board and say, oh, well, yeah, see, now I know the answer, I do that. Well, no, I don't know. I mean, it's hard. And so I get my critical numbers that way, and now I can look at f double prime of x, you know, and it gets really crowded in there and all that, but you know, I can see that it is positive from, well, actually I can't see that. Okay, there, I'm starting to see that it's positive. Okay, so let me go back to this one, and you know, there it's 0, and it's 0 here again at 5 pi over 6, and there again, things are getting really crowded. I could go here and keep my y values, but my x value, you know, just have that go to 3.2 or something like that, and start this one at maybe minus 0.5. And so then I can see things a little better, and you know, so there's 0, 0. There's pi over 6 and 0, 1.173 and 0, and so here, what's I guess nice to see really, although it doesn't affect us too much in the problem. Well, although I guess the book did ask for inflection points, I think. Yeah, so it did want inflection points. So when you look at this one, you know, we've got 0 and pi over 6. Those are nice numbers. But, you know, these others, and I didn't get to maybe the last one or two, you know, 1.173, 1.968. So, you know, those are not great numbers. Now, there's a 5 pi over 6, and there's a pi and 0. So we have all these pieces, and so I can keep track of it, and as I look at it, so now we want to name various things, and looking at the red one here, you know, I see that I had a maximum, a relative maximum here, and that was, I don't remember what that number was, but we had a single relative maximum, and then, you know, and we can tell it's a maximum because it's concave down. We can see the green here with the second derivative, concave down, and you know, so that would help us there with that second derivative test. All these others look like they might be inflection points. Okay, so and I can check that because I can see the concavity does change at those points. Okay, so I found a bunch of inflection points. So one inflection point is at pi over 6 and 0. Now, here we're at the edge. 0 is an inflection point, but in some ways it's kind of hard to tell unless I go beyond the original 0 pi bounds to really see it. And then the same thing at pi. It is an inflection point, but I have to kind of look for that. And it's just interesting in that, you know, here at this point, oh no, never mind. That's not what I wanted. That's the y value. Yeah, at this point, we have that the derivative is 0, whoops, and the concavity does change. And so that's where, when you look at that, if you're doing a second derivative test, it actually didn't tell you anything. Okay, because it says the derivative is 0, but so is the second derivative. Well, without looking at it to actually see that the concavity is changing, and I can see that really well with the green curve because it goes from negative to positive. Without that, if all I knew was the derivative was 0 and the second derivative was 0, I don't know what I have. Okay, I don't know if it's a point of inflection, a relative max, a relative min, or none of the above. Okay, and so, you know, I would need other information. In this case, you could say by looking at the graph, I'm checking the concavity of either side of the point, and I see the concavity changes, so that, oh, okay, that tells me I have a point of inflection. I can check the derivative, and as I look at the blue curve, I see the derivative is positive on both sides. Oh, so a first derivative test would tell me that the function's increasing, then gets flat for just the moment, and then is increasing again. That is not a relative max or min. Okay, because the derivative is positive on both sides of the point. And so I can get all that information, but again, this idea of, you know, take the derivative, set it equal to 0, get that, then use the second derivative to determine concavity at that point for a relative max or min, well, it's not surefire, okay? Because, well, if they're both 0, I don't know what I have. I could have either, and so I might be stuck at that point. Well, sort of stuck. I have to check the derivative at different points or just check the concavity. Okay, and that's really what we're doing with the graph. More questions on that? So I did not actually find the second derivative. I could do that pretty simply. If I couldn't, right, the other thing I can do is I can go in here and, well, actually, Sage Math Cell. So I could go to a Sage cell and pretty quickly type this stuff in. So I say var, open parentheses, and a quotation mark x, like that. And f equals, and what's my sign of x? So here I have to be a little more careful about symbols and all that. So I actually need the parentheses around the sign of x, and then minus, and I have 1/3 sine of x, sine of 3x. So I'll probably, the simplest way to do that in here would be, now notice I have to put the asterisk for the times, and then divided by 3, and then plus sine of 5 times x, and divided by 5. And so there's that. And then I could take the derivative and call it fp maybe equals f dot diff with respect to x, so I tell it of x there. And I could take the second derivative by taking the derivative of the first derivative. And so I do that. And then I can show each of these. Now I believe I could do show f, comma, fp, comma, but it may not look too good. Let's try it. F, comma, fp, comma, fpp there. And we'll see how it looks. Yeah, see, it just sets one next to the other, so that's a bad way to go. And so we'll do each one separately and show that one and evaluate that. And it does it in a little different order than I had it, but there we go. We have our derivatives. And now you can even, I did exercise 46 in a video, and I went so far as to then actually solve the derivative, set the derivative equal to 0 and solve for x. Right? So I could do that. I'm looking for critical numbers, and I say c equals, and it'll be interesting to see how it does on this. On number 46, it didn't do any better than I did, which was not good. I mean, I didn't get anywhere. But c equals, and I'll just say solve. And so what do I want to solve? I want to solve fp equals, two equal signs to talk about true equality, equals 0. And I want to solve that for x. And then I'll show that solution and evaluate. And we'll see it if it, yeah, see, it doesn't do so well either. Which is, again, really amazing to me with Desmos that it does better than Sage Math here, in that, but it seems to do it numerically, yet knows that you get these really nice numbers like pi over 6. That's just amazing to me that it does that. So, but yeah, see, this didn't do any better than I would have done. Okay. Questions on any more on that? Okay, so that's the idea. Now, and I would like to point out that if I do something in class and you haven't done that problem yet, well, one, it doesn't hurt to then, try it without using notes or something along those lines. So you just go ahead and you try it again without looking at anything. And the other is, well, try a different problem. See how it goes from the same set, that kind of thing. So, okay, any other questions on any of the material right now? Okay. So at this point, what we can do, if we're trying to simply find relative extrema, and then maybe check those to see, of the relative extrema, what are the, the absolute extrema among those, if there are any. So we're given some function. And then what we tend to do is we first, to find our critical numbers, we can look at two things. We can take the derivative, set f prime of x equals 0, find x values. Okay, so there we can get critical numbers that way. And again, this, as we see with Desmos, probably any of the book problems that we're going to have, this is actually not a hard thing to do. Right? So I would love to see you all have wonderful symbol pushing skills and jump around on a page with those symbols and get it all right and do all that. But in the end, right, if you're given the function and you have access to Desmos, this is a piece of cake. You literally could write this, I think, and it will just give you those numbers as vertical lines on the graph. Okay, and you'll have to still go see where they cross the x-axis. But I think if you actually put in the equal 0, it would just make a bunch of vertical lines. Now, that's where I would just have it graph f prime of x and look for where it crosses the x-axis. But I think, typing that in will work. And so, to a lot of extent, it shouldn't be a problem, right? We should just be able to make this happen. And then to go further, well, if you want to know the formulas and so on, well, you've got Sage Math, and you can type stuff in there, and it'll give you a formula. So we set that equal to 0, find those x values. That's possible critical numbers. And then the other is find where f prime of x is undefined. What's not in its domain. And find those. Now, actually, that can be the harder thing to do, possibly. Because you could have things like removable, as we saw them, removable discontinuities, removable singularities, and they wouldn't show up on the graph real well. But generally, yeah, again, most of the functions we would deal with, you can find this. It'll be there. And probably, in many cases, the reason f prime is undefined was that f was undefined to begin with at that spot. Okay, so there we find our critical numbers, and then once we have those things, then we can look at, say, the second derivative, so determine f double prime of, I'm going to call it x sub c, where x sub c is a critical number. Now, of course, this only works for the part A ones, right? Because if the derivative's not defined, neither is the second derivative. So I can only do this for the place where f prime is 0. But determine this, and I'm either going to get f double prime xc is negative, in which case, the text tells us, it goes through things, we've talked about it a little bit, that when you have a negative second derivative, that's concave down. So we know we've got something that looks like that. We could have f double prime of that critical number being greater than 0, in which case we know we have that. And then finally, we could have that thing equaling 0, in which case I'm not sure what's going on. Okay, and I would need some more information. And so that's the second derivative test, and it's really nice. But of course, you may or may not want to use that because maybe that second derivative is a real pain to either calculate to begin with or evaluate. Now, once again, you can go to Desmos or Sage or something like that to get them to do it for you. So these are all possible things to do. We can look at graphs and that sort of thing. But that's what you want to do. And these are the steps I want you to understand and understand why you're doing them. Okay, so looking at the concavity again, well, I know I might be here or here because I already knew the slope was 0, and so if it's concave down, I must be at a maximum. If it's concave up, I must be at a minimum. And then, of course, again, well, if it's 0, I just don't know because, well, this could flatten out enough just momentarily to be still essentially concave down around it, but not right at that point. So it might still be a maximum or a minimum, but it could be an inflection point. Or again, it might be neither if I came up with a crazy enough function. And, so this is the basic idea, and then you probably need to keep going if this is the case, or if you didn't want to do this sort of second step to begin with, right? You might, check f prime of x on each side of the xc that you're working with. Again, that's usually you're going to want to do something like that if you have that at the very least, and so that can help you with the relative extrema that way. Okay. So there's not much to it, and if you think about doing it with the help of technology, I mean, it should become pretty quick to just make it happen and check things. Okay, if you do a little bit of practice, especially with the technology, you should find it's just not a big deal. The big deal is when we throw all the algebra and trig at you to push things around, because then it's easy to get lost in what you're doing. And in that way, that's one thing I like about technology is you can concentrate on the steps and not get lost in all the algebra and trig. And then once you're really comfortable with the steps, well then, you know, getting mired down in the algebra and trig, maybe you want to or need to do that because you've got a complicated enough problem, but you don't get lost because you know where you are in the sense of the problem as a whole. You say, oh, well, I'm just trying to figure out where this thing's zero. Okay, and that might seem like an impossible task, but that's all you're doing as far as this whole big thing. Okay. So questions on that? It's kind of where we are at this point. Okay, well, in 3.6, I have to find the sheet. I'm pretty sure I have one that's already made, but here's the idea now is kind of what I want you to be able to do out of 3.6 or thinking about what 3.6 is trying to help us do. So 3.6, you know, they're talking about curve sketching. And to me, what we're doing is we're just really, really learning to translate between a graph and numbers. Sort of symbols as well, because you know, we would write it as symbols. So suppose I have some function, and how many of these do I have? 1, 2, 3, 4. And what I figured out, I'm not going to worry about what's going on right at those spots, but we would probably have that information as well. But in each of these sections, you know, I may know that f is positive, f prime is negative, and f double prime is positive. So possibly I know that. Now, how would I know that? Well, I have the function, I've taken its derivative and so forth, and you know, each of these spots, what are these? These are probably critical numbers, but both zero order, so it might be where the function itself is 0 or undefined. It might be first order, the derivative is 0 or undefined. It might be second order, the second derivative is 0 or undefined. But, you know, I found those points, and in between, this is what I know. And, you know, so maybe f is greater than 0 there, f prime is less than 0 here. Oh, wait, is that? No, sorry. F is less than 0, we'll say. And then f double prime is greater than 0. And in here, I know that f is less than 0, f prime is greater than 0, and f double prime is, say, greater than 0. And f here is greater than 0. F prime is greater than 0, and f double prime is less than 0. And then here, finally, f is greater than 0, f prime is greater than 0, and f double prime is greater than 0. So this is kind of one of the things I'd like you to be able to do is, you know, if you've just got this kind of tabular information, can you get an idea of what the function might kind of look like? And so, you know, as I look at this, right, and I'm going to come over here and I guess redraw it. So 1, 2, 3, 4. So I've got room to go above or below. But so this says f is positive. Oh, okay. So I'm up here somewhere. It says the derivative is negative. Oh, so I have to be coming down. And then it says it's concave up. So it does something like that. Everybody agree with that? It's positive everywhere, it's decreasing, and it's concave up. So I just do that, and then here, well, it's negative, but the other two things are the same. It's still decreasing and it's concave up. So now it looks like that. Then, middle one, it's still negative, so I'll be below the line. But now it's increasing and concave up. So there's increasing concave up, and it's negative. And then positive, increasing, concave down. Okay, up here, so it's positive. Increasing, so it's got to go up like this, but concave down, and so it looks kind of like that. And then finally, positive, increasing, concave up. And, well, I'd probably just put it like that. But now, as I look at that, if I were to then try to draw this thing, now I don't know where the y-axis is, but if I were to try to draw this thing, it looks like it sort of comes down like that, starts going back up, it looks like an inflection point there at 0, 0, or well, not 0, 0, something 0. And then maybe another inflection point there and goes up like that. So there is kind of what I might be able to piece together for this function. Now I'd have to have much more information to know for sure this is what's going on, but probably with the nice functions we have, yep, that's probably what's happened. And I would have to get a little more information to know, what that value is. And of course the x values along here. But that's one thing I'd like you to be able to do, is just take tabular information like this. And again, I could add a little more. I could tell you that right here, where is that point? That was, I did the second one in. So, right here I could tell you at x equals 5 or something like that, f of x is 0. F of 5 is 0. So I could give you information along those lines. Questions about this idea of the tabular? Okay, so, if I'm given all three pieces, I should always be able to draw little segments like this that do all those things. Now, if I'm only given a couple of the pieces, if I didn't tell you here about what the derivative was, well, I wouldn't know for sure, is it increasing or decreasing? So if I didn't tell you that one, well, it could have looked like that, or it could have been decreasing and concave down, and so it might have looked like that. I wouldn't know. I'd have to hopefully get some other information like, oh, the function's continuous, and some things like that. But as much information as I have on any given interval, I can always draw those pieces like that. Okay, questions on that? Okay, and then what that's related to is another task. Again, these are really just drill sorts of things. is that I could draw various things. So for instance, let's start with, suppose I tell you that's f of x. Can you draw f prime of x and f double prime of x? At least reasonably, right? Well, so I have to look at the picture and essentially look for those things, right? Look for critical numbers. Where is the derivative 0 and where do things change? And so I guess the way I drew it, it looks like x equals 0 is a critical number. Okay, because the derivative is 0 there. Any questions about that? And here, I don't know what this x value is, but there's another critical number because the derivative looks to be 0 there. And then I can look at the derivative itself and, okay, here it's positive. All my derivative values need to be above the x-axis. But they have to make it to here. So it's got to come down like that to 0. Now, does it really have to come way down like, well, this is steeper than that, and so it should be a bigger number. Right? So the derivative is coming down like that. Now, then here, the derivative is negative. Okay, so I have to be below the x-axis, but it has to come back to 0 at these two spots. So I have to be down here, but I have to get back to the x-axis. And as long as everything's continuous and so forth, yeah, that's what it would have to look like, something like that. And then it's positive again. So it heads up like that, and there's f prime of x. And then I could ask for f double prime of x. Well, it's just drawing the derivative of the derivative. That's one way to look at it. Or you could look at concavity and look at it that way. So if I look at it as the derivative of the derivative, you know, here's the derivative. And, well, so where's the critical number for that derivative, right? Oh, right about there, maybe. And that's where I hit a minimum. And before that, the slope of the derivative is always negative. Okay, so, you know, that's always negative, but it's got to get up to there. And then after that, the slope of this is always positive and getting bigger, and so it heads off like that, and this looks like f double prime of x. Now, if you also then compare that to the concavity, I think I did okay, because here, concave down everywhere in there, so the second derivative should be negative, and it is. Then concave up everywhere in here, and so the second derivative should be positive, and it is. Okay. Usually for most of us, I think it takes a bit of practice to do this. Now, what I have to look for, I started an interactive thing with this, and actually if you Google, I think, drawing derivatives or something along those lines, you could probably guess that way. The interactive thing I was making, the way it worked, was simply, I think it gave you one of various things, you know, the derivative, the function, or something like that. And then it just gave you a bunch of linked dots, and you could grab the dot. It's in Desmos, and you could grab the dots to make the right shape. And then when you click the answer, it just graphs the derivative for you. And so you can look, you know, and so, you could kind of do that yourself in Desmos, right? You could just pick a function out of the book, look at its graph and say, well, I'm going to try to draw its derivative in here. Okay, so that's drawing, starting with the function, but there's f prime of x. What's f of x look like? Okay, f double prime, for this one, hopefully drawing f double prime shouldn't be too hard because we've got the answer over here, right? I mean, this was just our original f of x, and now I'm saying, hey, this is the derivative. Let's try to draw the function. Well, if I am trying to draw the function, then I have to look here. Here are the critical numbers of the function. And so right now, of the function, when I look at the function, what I know is it had to be flat at those spots. Now the question is, where do I move those flat lines to be relatively correct for this? And notice the derivative is negative here. That meant I was decreasing to that flat spot. Okay, the derivative is negative. I was decreasing to that flat spot. And then, after I hit that flat spot, the derivative is positive all this way, so I'm increasing. Oh, okay. Now, I could leave this flat spot right here. Doesn't really matter for this first one. But, nobody tells me anything about the function. I don't know if it was positive or negative or what. So I could put it here. I could put that flat spot there, and you can't argue with it. Well, you can argue with it, but you would be silly for doing so. Okay? So I was decreasing. Now notice I'm not even worrying about concavity to get this thing started. I was decreasing down to there, and then I was increasing. But it's got to increase all the way until here, so, there it's increasing. And then I had another flat spot. And then the derivative was negative. It's negative down here. So it was decreasing again. And, well, if I did that, then I don't have to move my little flat spot. Okay. But I didn't have to put it, I could have put it down here. I could have put it up there. There's nothing that really tells me one or the other. And so right now, the function looks like that. And then, the derivative is positive again, so it's increasing again. So it kind of makes a W. Now, so this is my f of x. Now I can then round it out a little bit to make it look better. Okay, but I'm really just kind of looking at where is it increasing, where is it decreasing, and where did it have to bottom out or something like that. Questions on that? Anything? This is definitely a much harder task for most of us. And it takes some practice. Okay? But it is, I think it's a really important thing to be able to do because you want to be able to look at a graph and really synthesize what's going on. And also if you can read graphs better, you can probably also make graphs better. So if you have to convey some information, you might be much better at creating a nice graphic to really help somebody understand what's going on. Any questions on any of that? Alrighty then. Well, then I'll see you on Monday, and have a lovely weekend.